Good afternoon to good afternoon to all of you. So today we are going to start. This is a new chapter. That one is called as boundary layer theory. This one is called as boundary layer theory. Is my voice is audible? If it is okay, then we'll start now. My voice is audible to all of you? Yes, fine, it's okay. So today we are going to start a new topic that is called boundary layer theory. Let me bold this one. Okay, so this one is called as boundary layer theory. Okay, so boundary layer theory. So what do you mean by boundary layer theory? Okay, so first of all you should understand that one. So when a fluid flow past a object, what will happen? There is two region will be formed. Okay, in one zone, in one region the viscous flow will be exist. In another region there is no inviscid region will be exist. Means there is viscosity will be 0. Okay, so suppose this one is a plate. Suppose this one is a plate. Okay, this one is a plate. When this one free stream velocity, what do you mean by this free stream velocity? Okay, what do you mean by free stream? Free stream means what? The stream which has constant amount of velocity. Okay, and the stream which is not come in with contact with the solid surface. Okay, that is called as free stream velocity. I mean there is the velocity will be uniform throughout the depth. Throughout this y-axis the velocity will remain constant. Okay, and that one is not come contact with this solid surface. This one is solid surface. Okay, so what will happen when this free stream will come contact with this solid surface? The very first layer of the fluid, which is narrow to the solid surface, this one is called as solid surface. Okay, so the very near layer of the fluid which is just near the solid surface, what is the velocity of the fluid particle there? The velocity of the fluid particle will be 0 right over there. So due to the van der Waals force of attraction, or I can say due to the adhesive force in between this water molecule and the solid surface, so that nearer to this one, the velocity of the fluid particle will become 0. Okay, so suppose I am choosing any one fixed point. Suppose I am choosing this point as A. Okay, so what will happen? I am at this point A. So at this point the velocity of the fluid particle will be 0. Okay, at this point A the velocity of the fluid particle will be 0. Now if you move, in perpendicular direction, if you move in perpendicular direction from this plate, the velocity will now gradually it will increase. Okay, so now the velocity will be gradually it will increase. So what actually I want to say, so a velocity gradient will be exist. Okay, now the velocity gradient will be exist. Okay, and after this one we'll find a layer of the fluid where the velocity of that layer will be equal to 99% of the free stream velocity of this layer. At this point A will be equal to 99% of the free stream velocity. Okay, and that if you join all these points, suppose I am choosing another point B. Okay, there will also I will find a point where this velocity at that point will be equal to the free stream velocity. If you join all these points, a layer will be formed, a line will be formed. That line is called as boundary layer line. Okay, so now this one is a velocity gradient. Okay, so as I move away gradually from the wall, the velocity increases gradually in perpendicular direction. Okay, So I can write down one point here. So whatever I said, right, I'm writing it down. So when the very first when the very first layer of the fluid, when the very first layer of the fluid that comes in contact with the solid surface, that comes in contact with the solid surface. Okay, so what will happen? Due to the van der Waals force of attraction, due to the van der Waals force of attraction, or I can say due to the adhesive force, in between this water molecules, water layer and the solid surface, what will happen? The water will stick to this, the water will stick, it will just stick to the solid surface. It will just make a layer, it will just at a rest in that solid surface, that will stick to the solid surface. Okay, solid surface, and that is known as called non-slip condition. That one is called as non-slip condition. Okay, where this velocity of this particle will be 0, that one is called as non-slip condition. Okay, non-slip condition. So I'm trying to say, so this is the first point. Second point, what I said, as I move away from this wall, if I move away from this wall perpendicular, if I move perpendicularly away from this wall, what will happen? The velocity is increases gradually. The velocity now it is increasing gradually in perpendicular direction. Okay, so I can observe one point is that each and every layer has a different velocity. Okay, each and every layer has different velocities. Okay, so there is a zone where the relative velocity will exist, what actually I'm trying to say. So in second point, I can write down just simple language, I'm trying to explain you. So second point, as I move away gradually from the solid surface, from the wall of the solid surface, I can better recognize, from the wall of the solid surface, what will happen? The velocity increases gradually. The velocity of this water, of this flow, whatever the fluid is there, the velocity increases gradually. The velocity increases gradually in this perpendicular direction. Okay, in perpendicular direction. Okay, so I can observe what actually I observe. So what I observe, there is a relative velocity will come into this zone. Okay, so I can write down, so I can observe that, so I can observe that there is a, so I can observe that each and every layer has different velocity. Each and every layer has different velocities. You write down, then I will explain you so that you will get clarity. So what is I'm trying to say? So there is a zone where the relative velocity will exist. So there is a zone where relative velocity exists, where this relative velocity will exist. Okay, so what actually I'm trying to say, just understand this point. Let me make you understand. Yes. Okay, so this is my plate. Okay, this is my plate. and this is my free stream velocity, which is not in contact with this solid surface. This is my free stream velocity, okay, which is constant velocity. Now if it is come in contact with this solid surface, what will happen? Suppose at this point, what I'm trying to say, at this point A, the layer of the fluid which is in contact with solid surface, that layer has zero velocity. But if you move perpendicular direction away from this point, the velocity is now, it is gradually increasing. And see, each layer has different velocities. Each layer has different velocity. If there is a different velocity will be there with respect to in perpendicular direction, this is my perpendicular direction, what will happen? There a velocity gradient will exist. Okay, so within this zone the velocity gradient will be exist. But after traveling some distance from this wall, will reach one point. Suppose this point this is point B. So at this point, this layer has a velocity which is equal to 99% of the free stream velocity. Okay, that is equal to 99% of the free stream velocity. That is actually, so write down third point. So one point will come where the magnitude of velocity that is equals to 99% of the free stream velocity. Okay, what is this U infinite? This is called free stream velocity. Okay, free stream velocity. Okay, that is I am trying to say. Now what actually I am trying to say so now if you move, now if I move along the length of the plate, suppose now I am choosing another point. Suppose this point is now C. Okay, so there also I will find a point where this point, suppose this point is D. At this point D also the velocity will be equal to 99% of the free stream velocity. So if I move along this length of the plate, this is along the length direction. Okay, if I move along the length direction of the plate, what will happen? I will find some point where there is a velocity at that point will be equal to 99% of the free stream velocity. Okay, so now if I move along the length of the plate in perpendicular direction, if along the length of the plate in perpendicular direction, I will find the point where the velocity will be equal to 99% of the free stream velocity. Suppose at this point, C point, I got this point where the velocity will be equal to 99% of the free stream velocity. Again I moved at this point D point in perpendicular, again I found this point where the free stream of the where this velocity of this particle will be equal to 99% of the free stream velocity. Now there is, I found what? There is a locus of point I found. So this point, this point, this point. Now if I join all this point, a line I got. Okay, that line is called as boundary layer. That line will be called as boundary layer. Okay, so then third point I am trying to say you. So third point, now if I move along, please concentrate here. Now if I move along the length of the plate, in perpendicular direction, what actually I observe? I will find some points. I'll find this point. I will find the point where this velocity will be equal to 99% of the free stream velocity. What is trying to say? Suppose this is my length of the plate. So suppose at this point I found at this layer of the fluid, the velocity will be equal to 99% of the free stream velocity. Now again if I move in this perpendicular direction, suppose at this perpendicular direction I found this one as a point where what will happen? The velocity will be equal to 99% of the free stream velocity. Similarly I will find this point, So this point are generally called as where the velocity will be equal to 99%. It is not equal to, it's just equal to 99% of the free stream velocity. Now if you join all this point, this is called as my boundary layer. This is my called as boundary layer. Okay, so now I can write down, if now I join, if now I join the locus of the point where the velocity will be equal to 99% of the free stream velocity, the line joining this point, the line joining these points is called as boundary layer. That is called as boundary layer. Okay, so this is called as boundary layer. If I move in perpendicular direction every point, so I found some points where the velocity will be equal to 99% of the free stream velocity. Okay, so now I can conclude, observe something, why actually are doing this boundary layer. Okay, suppose when a car is moving, so the free stream velocity means the air. When the air will be come in contact with this car, what will happen? There is a boundary layer will be formed. What is the importance of this boundary layer? So now I'm going to say what is the importance. So so this is my plate. Okay, this is my plate, solid surface, and this is my free stream velocity. Okay, this is my free stream velocity. This is my free stream velocity. So now when it is when it flow fast with the solid surface, what will happen? A boundary layer will be formed. If you join all this point are called as where the velocity will be equal to 99% of the free stream velocity. Okay, 99% of the free stream velocity. Now actually I found a point. Suppose I am choosing this point A. Suppose this point A. If I move in perpendicular direction, so different layer has a different velocity, different layer has a different velocity. Okay, now if you join all this one, you will get a velocity gradient. So at this point, at this top surface, what will happen? The velocity will be of that layer will be equal to 99% of the free stream velocity. Means almost it will become constant. But if you observe, there is a two zone. One zone is outside of the boundary layer, and this zone is called inside of the boundary layer. This is outside of the boundary layer, this is inside of the boundary layer. So inside of the boundary layer, if you see within this boundary layer, first one is within the boundary layer region. So within this boundary layer, so if you observe within this boundary layer, what will happen? There is a relative velocity exist. See the velocity gradient, velocity is now it is changing with respect to this y direction. Suppose this is my y direction. If I choose this is my y direction, there is a relative velocity is there. Velocity are of this layer will be not equal to that layer. So there what will happen? Within this boundary layer, a relative velocity exist. Okay, within this boundary layer, a relative velocity will exist. I mean I can say this du will exist. The change in velocity will be exist. If there is a relative velocity will be exist, then there will velocity gradient also will be exist. The velocity is changing with respect to this y. Okay, the velocity is changing with respect to this y. So I can say du by this dy is exist. Okay, du by dy exist. If du by dy will exist, then I can say what I can say, the shear stress according to Newton's law of viscosity, I can say tau will be equal to mu into this du by dy. Okay, so what I can say, then tau also exist. Means what I'm trying to say, so within this boundary layer, as there is a relative velocity exist, so there is a velocity gradient is exist, so as a consequence a shear stress will be exist. So what is saying, there is a viscous flow will exist. Means it will give resistance when the car is moving in opposite to this flow direction, so there will be viscous flow within this region will happen. So that there is will be that region will give a drag force. It will oppose the movement of the car. So have you seen? So most of the car which are in streamline manner, which are very streamline, like this streamline. So what will happen, this boundary layer formation will be very less. The boundary layer formation will be very less. So what will happen, we can avoid the formation of the viscous resistance due to this boundary layer. Okay, that is I am trying to say. So now this is the within this boundary layer. What will happen outside of this boundary layer? Okay, what will happen outside of the boundary layer? So now B outside of the boundary layer. Outside of the boundary layer, what will happen outside of the boundary layer? The velocity is almost equal to 99% of the free stream velocity, almost equal to. Okay, almost equal to 99% of the free stream velocity means what? There is no relative velocity exist. Okay, so if you see practically, the relative velocity is exist, but that is very negligible. That we can neglect. That is very small in magnitude. Okay, so we can say practically there is exist, but the relative velocity, which outside of this boundary layer is negligible. Okay, negligible means this change in velocity almost will be equal to 0. Change in velocity will be equal to 0. As there is a relative velocity is not exists, so I can say there is velocity gradient also not exist, means 0. If the velocity gradient is exists, shear stress also does not exist. Shear stress also will be 0. Okay, so outside of the boundary layer, what will happen? There is inviscid flow, means that is there will be no viscous flow will be there. Okay, outside of boundary layer, no viscous flow will be there. Okay, so from this I can define boundary layer as, so boundary layer is the region, please listen carefully, boundary layer is the region in the flow field where fluid flows with a higher relative velocity, or I can say the layer inside this boundary layer has a relative motion in between this fluid particle. So if I can write down this definition of the boundary layer from this point of view. So what is this boundary layer definition? Okay, so boundary layer, is the region, the boundary layer is the region, the boundary layer is the region in the flow field, boundary layer is the region in the flow field, okay, where inside this boundary layer, a higher relative velocity exists, a higher relative velocity exists, a higher relative velocity will be exist. Okay, so that is the thing. So within this boundary layer I can say, so within this boundary layer what will happen, the relative velocity will exist, so this is exist, so I can say there is a velocity gradient will be exist. Okay, so this is du by dy as it exists, so tau will be equal to mu into this du by dy, so this is also exist, means within this boundary layer there will be a viscous flow will be there. So outside of the boundary layer what will happen? So outside of the boundary layer relative velocity is 0, so as the relative velocity will be 0, the shear stress also will be 0. Shear stress will be 0. This is the thing I want to talk you. So what is the inside the boundary layer? What is, so inside this boundary layer relative velocities exist, so as a consequence shear stress will be exist. So inside this boundary layer viscous flow is exist. Okay, inside this boundary layer viscous flow is exist. If the fluid flowing over the solid surface, okay, if the fluid which is flowing over the solid surface, that is incompressible nature. Okay, let me suppose this is my plate, over which the fluid is flowing. If that fluid, the fluid which is flowing, the free stream velocity, that one incompressible in nature, if that is incompressible nature, what will happen? The region outside of the boundary layer has a what? Inviscid flow. This is the boundary layer formation, na? So within this one will happen, this is viscous flow. This is called viscous flow. Outside of this boundary layer, what will happen? There is a inviscid region. Okay, inviscid region where the viscosity will be 0. So if the fluid will be incompressible, density will be constant. Okay, and the fluid outside of the boundary layer is inviscid. Okay, so inviscid, that is what is called, this is called as ideal fluid. That one is called as ideal fluid. Okay, that is called ideal fluid flow outside of the boundary layer. So that can I say that is the ideal fluid flow will be there. So inside this fluid boundary layer, what will happen? As there is a, as what will happen, there is a viscous flow will exist. So what will happen? The fluid particles, now it will spin around its own axis. The fluid particle will be spin around its own axis. Okay, so within this boundary layer, there is the fluid flow will be rotational fluid flow. Okay, already I have discussed this one. So inside this boundary layer, okay, the flow is rotational flow. Okay, but outside what will happen? But outside of the boundary layer, the flow will be as a irrotational flow. Okay, irrotational flow. Okay, and I can say the vorticity will be equal to 0 outside of the boundary layer. Okay, so as I told you, why that is fluid particle are spinning. Okay, so what will happen when this fluid particle, this is a viscous flow. Okay, if this is a viscous flow, in laminar flow, if the flow will be a viscous flow, what will happen? The fluid particle will rotate about its own axis. Okay, if the fluid will be viscous flow, inside this boundary layer, the fluid particle are rotating about its own axis. If the fluid particle will be rotating about its own axis, that is called as rotational flow. So inside this boundary layer, rotational flow will exist. Outside of the boundary layer, irrotational flow will be exist. Okay, that is actually I am trying to say. So now we understood about this boundary layer. Okay, now we understood about the boundary layer. Now we have to find out what is the thickness of the boundary layer. What is the thickness of this boundary layer? What is the thickness of the boundary layer? Okay, so try to understand. So this is my plate, solid surface, or this plate. This is the free stream velocity now, which will come in contact with this solid surface. This is my free stream velocity. Now when it is contact with one, a boundary layer will be formed. Okay, a boundary layer will be formed. Suppose now I am choosing any point. Suppose I am choosing this point as A. Okay, this point as a. So what will happen? This distance, the distance between the point which I have chosen as a point A, okay, where the velocity will be 0. At this point A, the velocity will be 0. So distance between this point A and the point, suppose this point B, where the velocity will be equal to 99% of the free stream velocity. So that distance is called as boundary layer thickness. This distance is called as boundary layer thickness. Okay, and this you see, observe this, the boundary layer thickness, is it constant? No, it is changing with changing in the distance from this plane. If you move along the length of the plane, if you move in this direction, x direction, this boundary layer thickness is keep on changing. Thickness is keep on changing. So I can conclude this boundary layer thickness is a function of x. Okay, so boundary layer thickness is a function of x. Okay, so at different value of x, if you start, this point is called as, so this point is called as leading edge. This is called as leading edge. Okay, and the last point of the plate, that is called as trailing edge. Okay, trailing edge. So if you move from this leading edge to trailing edge in this x direction, at different x value, what will happen? You will get boundary layer thickness different. So if the x will increase, if the x is increasing, so what will happen? The boundary layer thickness also will increases. The boundary layer thickness also will be increases. Okay. So that is the thing. Okay. And this boundary layer theory, actually this boundary layer theory, it has been investigated by one scientist, and he is called as the father of the boundary layer. He is called as the father of boundary layer, the father of the boundary layer, and his name is Pruntle. His name is Pruntle. Okay, he is the father of the boundary layer. So when this Pruntle is doing the investigation on this boundary layer theory, he told one conclusion that Pruntle thought that the flow occurs, the flow occurs on the solid surface, the flow which occurring on the solid surface. So initially the nature of the flow will be laminar. Initially the flow nature will be laminar. After certain period of time, the flow is gradually changing from this laminar to turbulent. Okay, so what actually Pruntle told? Okay, so this Pruntle, who is the father of the boundary layer, okay, Pruntle told that what he told, the flow okay, the flow initially okay, initially it is laminar in nature. It is laminar in nature, but as time moves on, the nature of the flow gradually changes from laminar to turbulent flow. Okay, so now what is this laminar flow is gradually changing to this turbulent flow. Okay, turbulent flow. So this zone where there is a transition is occurring, that zone is called as transitional flow. Okay, so it is converting from laminar to transition flow and transition to turbulent flow. So Pruntle told, if there is this one is solid surface of the plate, okay, when the free stream is come in contact with this solid surface, what will happen? The flow is gradually, it is changing to, so this zone from this leading edge, this is called as leading edge. So this zone is called as laminar zone. Okay, this is called as laminar flow. Okay, so if you move, this is the plate. Okay, this one is my plate, solid plate, and this zone is called as this is called as transitional flow, and after the transitional flow, the flow now become, it is turbulent flow. Okay, so what actually I'm trying to say, now we will actually study this boundary layer theory, okay, in two parts. One part we will study about this laminar flow boundary layer, and one we study as turbulent flow boundary layer. Okay, so in order to define this nature of the flow, what I told, one number has been introduced, that is called Reynolds number. Okay, so Reynolds number you have to find out. So Reynolds number will be what? This is rho u infinity into L by this is mu. Okay, what is this L? L is called as, this is characteristic length. Okay, this L is called as, this is characteristic length. Okay, for this boundary layer, this L is generally, it is measured in this length direction of the plate, along the length direction of the plate. So this characteristic length in this boundary layer, it is taken as x, which is length of the plate. This is length of the plate along the direction of flow, okay. So this is the Reynolds number formula by which you can find out the value, okay, so that we can find out the nature of the flow. So you can observe, if this length is increasing, okay, what will happen? The Reynolds number also increasing, okay. Means if the length along this increasing, the Reynolds number is increasing, means the laminar flow is now gradually it is converting into the turbulent flow. Now what is the point? At what particular value of the Reynolds number the flow will become turbulent flow? So that Reynolds number is called as critical Reynolds number. That Reynolds number is called as critical Reynolds number. Okay. So critical Reynolds number is what? At that Reynolds number, the flow is just becoming turbulent flow. Okay. So the critical Reynolds number value for this plate, okay, for this plate, it has been found that the value is 5 into this is 10 to the power 5. Okay, this is for solid plate. Okay, this is for solid plate. So if the Reynolds number is greater than this critical Reynolds number, what will happen? The flow will become turbulent flow. The flow will become turbulent flow. If the Reynolds number is less than this critical Reynolds number, that is called as laminar flow. That one is called as laminar flow. Okay. In order to decide the flow, whether it is to be laminar or turbulent, so you have to find out the Reynolds number. You have to check whether the Reynolds number is greater than 5 into 10 to the power 5 or it is less than 5 into 10 to the power 5. Then we can decide the nature of the flow. Now I can conclude one point is that what is the boundary layer? Boundary layer means when a flow passed a solid surface, okay, when a flow passed a solid surface, what will happen? At some point the velocity gradient will exist. Now the free stream velocity is not as it is free stream velocity. Now free stream velocity at every section of the plate is converted into the velocity gradient. Suppose this is my point A. Now the velocity is gradually increases with respect to this y. Okay, so every point I will get one velocity gradient, and every section, suppose this is point B, point C, so I will get a layer where the velocity of that layer will be equal to 99% of the free stream velocity. And if you join all these points, suppose this point I will get here, this point I will get here, so if you join all the points, a line will form. So that is called as boundary layer, which actually separate the two zone. This is zone 1 and this is zone 2. Inside this zone 1, what will happen? The viscous flow will exist. Inside this zone, the viscous flow will exist. And outside of the zone, what will happen? There will be inviscid. There is inviscid means there is no viscous flow. So viscosity, there is a inviscid region will exist. Okay, inviscid region. Okay, so within this viscous flow, what will happen? There is a shear stress will exist. Okay, if the shear stress will exist, whether it is a retardation or whether it will help when you are moving. When a car is moving, when the boundary layer will be formed, what will happen? Due to this turbulence, due to this viscous flow will exist inside this boundary layer, it will offer a resistance to the flow. Okay, it will offer a resistance to the flow. So in order to minimize this boundary layer thickness, what we are doing? We are actually making the thing very streamlined. Later on we will study. Okay, so if you move this is a dabba, if it is moving, what will happen? The boundary layer will form here. So it will retard the motion. It will retard the motion. Rather, if you make a streamlined body, it will make a streamlined body. If you see with this Hyundai car, streamlined body, what will happen? The boundary layer thickness is minimized. Okay, it is very less. It is almost zero. Okay, what will happen? It will not have a very significant resistance. It will not offer a significant resistance to the flow of this streamlined body. Okay, so in order to define, so we have to understand what is this boundary layer thickness, how we can measure this boundary layer thickness. Okay, in next class we'll study about this von Karman equation. Okay, von Karman equation, Blyus equation, how we can find out the determine this boundary layer thickness. A boundary layer thickness we can find out, then only you can decide. Okay, so in next class we will talk about this von Karman equation, displacement thickness, momentum thickness, energy thickness, what are the things there. Okay, so these are things how we can minimize this boundary layer. So boundary layer always to be avoided. Please keep in mind, this boundary layer thickness is always to be avoided. This is a negative to us. Okay, so always we have to suppress this boundary layer thickness. Okay, when the water is flowing in a pipe, okay, when there is a flow, due to the velocity will decrease, what will happen, there is a boundary layer will form. So what will happen, suppose you are designing for certain discharge of pipe, but due to the formation of certain length of the pipe boundary layer, so the flow will be retarded. So at the outlet of the pipe you will not get that amount of discharge. Okay, that is my objective. So boundary layer always to be avoided. How we can avoid it, how we can avoid, what are the methods are there, next class I'm going to talk about. Okay, so this is the thing, and today I'm giving you some assignment to you. Okay, so you just take this one as assignment and you try at your home. Try at your home. This is assignment for you. So try to solve this one as assignment. Okay, so please write down this numerical. This is assignment to you. In next class I will provide the solution of this assignment. Two numerical are there. Okay, please write down this numerical, and next class you just tell me the answer. What is the answer you got, you tell me. This one the previous year questions from your semester. These are the previous year question. If you can able to solve, it is well and good. Okay, please write down this numerical. So today only 24 students are watching. Only 24 students are watching. Thank you. So attendance will be valid for 2 minutes today. Only 2 minutes. So thank you all. Thank you for today, and tomorrow we'll meet again this time. So tomorrow I will discuss some numericals, engineering service problem, and this, so I will complete this boundary layer theory chapter. So thank you all, have a nice day. And the password of today attendance is, that is so the password of today attendance is, this one is 1205. This is the password of today attendance. Okay, and this is valid for 2 minutes today. This is valid for 2 minutes, and thank you all. Okay, so if you like my video, please like, share and subscribe. Okay, so thank you all, have a good day, enjoy. Okay, thank you.